Okay, so we want to extend the idea of vectors in R2 and R3 to Rn. As I said, we've done some of that already. Again, we're just going to consider a vector to be a tuple. In this case, we could call it an n-tuple. So it's just this list of elements. Of course, it's an ordered list of elements. If you switch the order, you have a different vector. For example, a 5-tuple is a vector in R5. An n plus 1 tuple, and I guess this has n plus 1 terms. Let's see. What are the terms? Let's say n is 5. Then we have, how many elements are going to be here? So 2n, it's just, 2n is 10, 8, 6, and so on. So I guess it's 5 elements. No, sorry, 6 elements. So if n is 5, there are going to be 6 elements if you go all the way down to 0. So that's why it's n plus 1. And we carry the same concept of equal, where a and b are equal if they have the same elements in each position. So ai equals bi for every I. We also extend the notion of vector addition and scalar multiplication easily. A plus b looks like this, and ka looks like this. And she says that you can prove these in a very similar way to the way we prove them in R2 or R3. And then we have the dot product like this. Then she says you can't really speak about vectors as arrows, though, anymore. So, nonetheless, she says the power of our algebra does enable us to define some geometric ideas, even for large n. So, for example, we can define the length of a vector. We had that this was the length for R2 and R3, and we can use the same. Since now we have the dot product in Rn, we can define the length for R. This was the distance between two vectors before, and we're going to use it this now as well. And the cosine, because we have the dot product in Rn, we can define this, and not the cosine, the angle between two vectors. And she mentions that, this should be between -1 and 1, because we expect that the cosine of whatever angle we have, so if we take the cosine of both sides of this, we get the cosine of theta. So if we take the cosine of the left side and the cosine of the right side, we get cosine of theta on the left, and we get the cosine of the inverse cosine of this stuff here. This stuff here is this stuff here. So, but the cosine of the inverse cosine is just like doing nothing. They're inverse functions, so that's like doing nothing. So you just get this part here. So this, if it's the cosine of the angle, this should be between, and cosines are always between between 1 and greater than or equal to -1. So that's what she said. This should be true, but at this point it's not clear that this is true. So we have to show that this is true, maybe. We will show that when we show this. We're going to show this in a minute. So now, even though we're not able to draw pictures of vectors, we can still talk about vectors being perpendicular, vectors being parallel, because we have this concept of angle, and also how far apart two vectors may be as well, the distance between two vectors. Okay, there's no simple generalization of the cross product. However, she says that if you look at these exercises, you can get something like a cross product for higher dimensions. Okay, we can create a standard basis of vectors in Rn that generalize the ijk basis So here we have the standard basis for Rn. So E1 will have a 1 in the first place and zeros for the rest. That's just like for I, in R3 we'd have 1, 0, 0. E2 will be 0, 1, and then zeros in the rest, and so on. And En will have 1 in the last place and zeros in the rest. And we're calling this a basis, which means that one of the implications of that is that given any vector in Rn, you can write it as a linear combination of these, but that's pretty easy to see. Given a vector A in Rn, then you can just do this. Take A1 times E1 and A2 times E2, so you're going to get this. Okay, now we want to talk about the Cauchy-Schwarz inequality, a very important and useful theorem, which says that if you take the magnitude of A and the magnitude of B and multiply them together, that's always going to be bigger than the magnitude of the dot product. Rather, I'm sorry, it's never going to be smaller. It could be equal to, but it's never going to be smaller than the magnitude or the absolute value of the dot product. So she says that if n is 2 or 3, this result is almost immediate. Let's look at in view of theorem 3.3, let's look at that. So you can see that the biggest that A dot B could be is when the biggest that the cosine can be is 1. So that means the biggest that A dot B could be is this, and it could be smaller than this. Okay, so however, we need a proof in the case of larger n, more dimensions. So first they say, note that if either A or B is 0, then this will work, and then this is true, because then you'll get 0 here is less than or equal to 0, so it's true. So now we can assume, we can test the cases where A and B are not 0, so we'll assume that they're not 0. Then we can define the projection of B onto A. So we have the dot product, so we can say that what we mean by the projection of B onto A is the same as we meant before in terms of this formula. And we can say that this is going to be a scalar, so it's going to be some scalar times A, which they've written like that. Now we're going to define C to be the displacement vector from Ka to B, right? That's what this means, right? So, in other words, B minus Ka, and then of course that means that B equals Ka plus C. Now she's going to show that this A dot C equals 0, and we can just follow the steps here. So A dot C equals A dot, this is C, so it equals that dot that, and then you can do A dot B and Ka dot A, and then you can do, actually it's actually A K dot A, but then you can switch the K to the front, so you get that. Now we said K just stood for this part here, so we just put that back in there, and so we get this, and then this now will cancel with this. We can do this kind of cancellation because everything in here, they're just numbers, they're just scalars, so you can cancel. So we get A dot B minus A dot B, which is 0. Okay, so anyway, we have 3 vectors. We have a C vector, we have a B vector, and we have a Ka vector, and the C vector goes from Ka to B. So all 3 of these form a triangle, and so and I guess, and I don't see why this is true, but I'm not going to think about it, but you can try and verify it. I guess that C, or rather, sorry, I guess that these 2 vectors are perpendicular. Wait a second. Sorry, this vector and this vector are perpendicular because they say that the Pythagorean theorem holds, and they ask us to check that as well, and Pythagorean theorem is when these two are perpendicular. So I guess that these are, we have to show that these are perpendicular, but so they say the Pythagorean theorem will hold here. Multiply this equation by a squared, the norm of a squared, which is a dot a, and you get this stuff here, and then this, so here we have this is this part, k was this part, so k squared is this thing squared, a squared, norm of a squared is here, so we get this. So I guess that, so then we write a dot a instead of this thing here, and then we can cancel, we have this is squared, so we can cancel these two, so we have a dot b squared plus this part here. So now what we had on the left side of the equal sign was this, and now we have this is equal to this plus this, and this is obviously not negative, so that means that the left-hand side is greater than or equal to this. That's what they say, the left-hand side is greater than or equal to that. Then taking the square root of both of these, we get what we were trying to prove, which was this. Okay? So that's called the Cauchy-Schwarz inequality. And that one way to think about it or remember it is that the norms of the two vectors multiplied is never going to be smaller than the dot product. So it's like if you want to change this dot to regular multiplication and put like basically absolute value signs around a and b, which we don't write absolute value, we write the norm. So we do that here. If you want to switch to that kind of multiplication, this part is never going to be smaller than doing it this way. Okay, and then this allows us to prove the very important triangle inequality. But before we do that, let's look at this. This is the picture that I wasn't thinking of or wasn't seeing. So yeah, this is the projection. The projection of B onto A is here. And then if I take that minus B, then this definitely will be perpendicular to this. So that isn't hard to see, I guess. Well, sorry, that isn't hard to see in 3 dimensions, or 2 dimensions, I mean. So I guess for n dimensions, we have to show that the angle will be 90 degrees. So we still have something to show. But I'm going to move on to the triangle inequality. So this is called the triangle inequality, and for vectors in R2, where we have just a regular triangle, then what you have is a vector A and a vector B, and the vector A plus B. So this might be A. This is not really A, but I'm just using this picture because it's sitting in front of me. This might be A, and then there might be another vector B. This is called C, but another vector B. And in this case, it doesn't have to be perpendicular. Just one vector here, and then maybe another vector over here, or another vector over here, or another vector over here. Anyway, we have these 2 vectors, one here and say this one. And what it's saying is, if you take the length of this one plus the length of this one, it's never going to be smaller than the length that connects the tips, the ends of these two, of the 2. Okay, so that's why it's called the triangle inequality, but that's just for R2, but we want to show this is true in Rn. Okay, before we do it, let's just quickly review this idea of norm. So what was, when we defined norm back here in wherever this was, chapter 1, where does it say chapter 1? Chapter 1. When we define norm, if this was when we had a vector in R3, then the length of A, also called the norm of the magnitude of A, and denoted by this. Now remember that the magnitude, usually we use absolute value just for a scalar, but when it's a vector, that doesn't mean anything. So this is kind of similar, or a generalization of that to vectors. So anyway, we said that the length of A, or the norm of the magnitude of A, is this. Okay, so this is the definition for the norm. But then we see that if you just do A dot A, you get the inside of this exactly, right? And so if you take the square root of A dot A, that means the square root of A dot A is the norm of A. So the square root of A dot A is the norm, or if you square this, you get that A dot A equals the norm squared, or the length squared. Okay, so I just wanted to review that before we continue with the triangle inequality. Okay, so let's try to prove this, the triangle inequality. So we start out looking at this thing, which we just said is A plus B dot A plus B. Right, we just said that the norm squared is equal to A dot B, so the norm of A plus B squared is equal to A plus B dot A plus B. Okay, so now we can multiply this out using some properties of dot products. So we're allowed to say that this is A dot A plus 2A dot B plus B dot B. Those were some of the we're using some of the properties that we discussed about dot products. Now this part here, because of what we just proved here, the Cauchy-Schwarz inequality says that this will never be smaller than the other one. So that means that this here will never be smaller than this part here, so we write less than or equal to here. Now we can say that A dot A here is the norm squared, and B dot B is the norm squared here. And now these are all numbers now, actually. Everything in here is a number, or rather, this is a length, this is a number. So we can just use regular algebra to collapse this like this. And then we can take square roots of both sides, and we get this, since the quantities on both sides of the inequality are non-negative. Right, this is not going to be negative, this is not going to be negative, so we can take the square root of both of them, and we get this. So again, in two dimensions, it says that the sides of a triangle, it says that the sum of the lengths of the two sides of a triangle must be at least as large as the length of the third side. So this picture here, this plus this has to be at least as big as this. That's what the triangle inequality says in 2 dimensions. But now we have it for n. Okay, so that will be important for us at some point to be able to use the triangle inequality, and maybe the Cauchy-Schwarz inequality as well. So next we want to talk about matrices.